is from Lab to Markets. I'm Rosanna Garcia. I'm here at the College of Business, and I'd like to just give a brief introduction to each of our speakers. And I have them ordered in regards to where they are from either in the lab into the market, and how our products will move from a lab into the marketplace and the issues that do come up. And so our first speaker, and if I actually read off the credentials of all of our speakers here, we'd have more time me reading who they are than we would have to introduce who they are. So I am going to keep it very brief and let you know this is just a very quick summation of who they are. Our first speaker is Dr. Ahmed Bousnaya, and he is the William Lincoln Smith Chair, Professor, and Director of the National Science Foundation Nanoscale Science and Engineering Center for High-Rate Nano Manufacturing and the NSF Center for Nano and Microcontamination Control at Northeastern University. So if you can remember that name of that, it'll be a test afterwards. He is internationally recognized for his work on nano and microscale defects, mitigation, and removal in semiconductor fabrication. He serves on a number of advisory boards, including Samsung Electronics, Chemical Industry Nanomaterials Roadmap, and he is listed in Who's Who in America in Science and Engineering, and is a Fulbright Senior Scholar among other honors. Our next speaker is Dr. Michael Knowles, and he is the Vice President of Global Scientific and Regulatory Affairs with the Coca-Cola Company, and he is Chairman of the CIAA Nanotechnology Task Force, and that CIAA, for those who didn't know, like myself, is the Confederation of the Food and Drink Industries of the EU. He's held positions with the UK Ministry of Agriculture, Fisheries, and Food Science Division. He is going to be talking to us about the food and drinks industry perspective on regulatory needs and gaps in the nano context, drawing on his experience from Coca-Cola and as a member of CIAA. We'll then have Dr. Seth Coe-Sullivan speak, and he is the co-founder and Chief Technology Officer of QD Vision, which is a nanomaterials product company delivering light and display solutions to companies. He has more than 20 papers and patents pending in the field of organic light emitting devices, quantum dot LEDs, and nanotech fabrication. He was awarded Technology Review Magazine TR35 Award in 2006, naming him one of the top 35 inventors under the age of 35. Dr. Coe-Sullivan is honored to sit on Brown University's Engineering Advisory Council. We have then Dr. Paul Schulte, who is the Director of the Education and Information Division and Manager of the Nanotechnology Research Center at the Centers for Disease Control and Prevention. He has conducted extensive research on occupational cancer and the roles of genetics in occupational safety and health. He is the editor of the textbook Molecular Epidemiology, Principles and Practice, and has served on numerous other journals. He is a consultant to agencies such as the International Agency for Research on Cancer, the National Academy of Sciences, and others. And will be followed up with Pat Roy Mooney, who is the Executive Director of the ETC Group. The ETC Group supports socially responsible developments of technology useful to the poor and marginalized, and it addresses international governance issues and corporate power. Their work expands to encompass a succession of emerging technologies, including nanotechnology. He has more than 4 decades experiencing work in international civil society, first addressing aid and development issues, and then focusing on food, agriculture, and commodity trades. He has a number of awards, and the one I thought was the most interesting is he has received the American Giraffe Award. It's for people who stick out their necks. So please welcome our committee. And we'll go ahead and start out with Dr. Bousnaya. If you'd like to move into the audience, please feel free to do that. I'd like to keep questions until the end of the speakers are finished.
So I will try to talk about the topic of nanomanufacturing, and I thought I usually start with something like a scale of what nano is, and I'm sure that all of you are familiar with this. And I thought, besides this, I want to explain what is nanomanufacturing. Most people think that by just making something that's typically very, very small is nanomanufacturing. So I'm going to just go through a few slides to explain what is nanomanufacturing. We all sort of, when we talk about manufacturing in general, we think of top-down manufacturing. You take a piece of metal, you take other metals to connect them, or a silicon wafer, you take it and etch it and make devices out of it. And this is what, there's a scale here, a very large scale on the right side, and then the small scale on the left side. But is that nanomanufacturing? Well, it is not. Nanomanufacturing basically is looking at the nanoscale size, but actually it's not doing it the traditional way. It's making things in a different way. When we make things, we produce a lot of waste, and we do things in a very bulky, inefficient way. And if you look at what inspires nanomanufacturing, it's really more like nature, basically. If you have the way nature does it without waste, very fast, precise, and builds things atom by atom. And that's what nanomanufacturing is. You build things bottom up. But to do that, you really need to have a guide. Nature has a DNA to guide the growth, whether you're talking about whatever thing you're talking about, a tree, you're talking about a plant, a human being, it's the same thing. It's built atom by atom. So in nanomanufacturing, we'd like to do that. And actually, that was made possible initially, very, very early in the 80s. And this is by invention of the STM and AFM scanning tunneling microscope and atomic force microscope, where for the first time it showed that you can actually manipulate atoms at the nanoscale and other nanobuilding blocks. But these are not manufacturing tools. For example, if you take atomic force microscope and use it to place carbon nanotubes to make let's say a memory device, a 1 gigabyte memory device, it will take you 400 million hours to make one layer of that device, not just the device. So we obviously need a better way to do this. So here at Northeastern, we actually have a center that looks at that and does assembly. I'm going to show you a couple of examples. Assembly at the nanoscale to produce three-dimensional structures, two-dimensional structures from nanoparticles, nanotubes, polymers, and so forth, and have applications in energy, electronics, and biomedical applications and materials. We also have an effort in environmental health and safety of nano materials. And I'm going to talk briefly about that. We don't have time to talk about all this. So basically, our mission is to look at the commercialization of nanoscale science research. To do that, we have to look at all these aspects. How can we be efficient? How can it be cost effective? How can it be safe? How it can be useful for society. So these are I have a couple of slides to show examples of nanoscale structures that we built. So this is on the far side. These are 10 nanometer particles. We can assemble down to 5 nanometer particles in any kind of structure, 3-dimensional or 2-dimensional to make circuits. The next one is polymers. We can assemble polymers very, very fast, but orders of magnitude faster than most people can over a large area. And very small structures. We can assemble nanotubes to do electronics, and we're already making a lot of different structures with this. You can do it over a very large surface, wafer level. You can do it on a polymer. You can do it on a variety of structures. So what is this good for? Well, this is the basic technology of nanomanufacturing, which is basically directing the assembly of nanoscale building blocks, or elements we call them, and transfer. And you can see that we have a very wide, diverse applications here. We have materials applications, We have energy applications, batteries, photovoltaics, and other energy harvesting tools, flexible electronics, non-volatile memory devices, much faster than the flash memory that you see today, for example. Biomedical, we have very early cancer detection, drug delivery. So a lot of these things are made possible because we can get tremendous capability by harnessing the properties of the nanoscale materials that we use. So, for example, this is just one. I'm using one example here. This is a biosensor that we make. The biosensor is 0.1 millimeter, the total size of the biosensor. It can detect up to 4 different biomarkers. And you can see that the student's holding the biosensor. The biosensor is glued on top of a catheter. The catheter is 0.3 millimeter in diameter. It has a detection limit that's more than 100 times lower than current detection limit. And yet it's very, very small, smaller than any device that you can get. So that is made possible by harnessing the assembly capabilities and also the properties of different of the properties of the nanomaterials at the nanoscale. So how diverse is this? What companies are interested in? You'd be surprised what companies are interested in, even the ones that do not make anything that you think even closely resembles nanotechnology. These are companies that are actually on our industrial advisory board. And as you can see, aerospace companies, there are 4 there. There are energy companies, solar energy companies, 2, 4 electronics companies, oil equipment company, instrumentation companies, 4 polymer companies, general energy company, chemical companies. So there's a very wide variety. They're all interested in one thing, which is the ability to assemble and control matter at the nanoscale and build and scale it up and make it fast so you can make products out of it. So we go back now to the health and safety. How safe is it, and how can we make sure that we handle this material safely and that we make sure that we know what material is toxic and what material is not. Unfortunately, we have there is no good way actually to scan all these nanomaterials because we have a very large number. So we have an effort in the center here to look at all these aspects. And Professor Jackie Isaacs, who was just moderating the panel before me, is in charge of this thrust area, which looks at the exposure assessment control, looks at the higher toxicity screening, end-of-life impact, environmental and economic uncertainties, regulatory issues, and social and ethical issues. I don't have a lot of time to go through that. I'm going to talk about one aspect, which is the higher toxicity screening. And the reason this is important is because nanomaterials nowadays, it's not enough to say nanotubes are toxic or nanotubes are safe, because nanotubes are the material that we make the nanotubes from, carbon. So it's what matters is on the surface. I can functionalize nanotubes in a way that makes them very safe. I can put them with cells. Now the cells die. I can functionalize them. I can make them in a different way where they'll be toxic. It's what's on the surface, and also that means that whoever's making those nanomaterials, if they change one step in the process, they could change what's on the surface, and that means the behavior will be completely different. And so, what should we do then? There are thousands of different nanomaterials, and each one of them will have a different surface interaction because of the way they're made. And so, one way that's been done now is to do a live assay, put these nanomaterials with cells and see how many of the cells die. And that will take about 3 to 4 days. Another way that we're working on, and other people are working on as well, mostly at universities, UCLA and Northeastern and UMass Lowell, basically. And one way is to look at a quick way to do this, and this looks at the oxidative stress of the materials. And what that means is you put it in a plasma serum, and you see what the oxidative activity is. And so, for example, the baseline is up there, so that means there's no oxidation activity there. And as you look, you see the nanosilver has some activities, and that's the arrow shows the increasing oxidative stress. And if you look at titania, for example, and silica and alumina, they show no activity. You go to carbon black, it shows some activity. You go fluorine, shows some activities. Nanotubes show some that have no activities, and some that has or very little activities, and some that has a lot of activities. And so basically we looked at that further. Now, the reason we're interested in this because this takes about 2 to 3 hours to do, which means that you can actually have it in an industrial setting where each batch that comes in is checked, and with a couple hours you will know how safe it is. And so, for example, one thing we dig further is that, well, why nanotubes are that we have that wide range? And one of the things we looked at is that we looked at some of the properties, surface area, metal impurities, morphology, surface charge, and so forth. And it turns out that the surface area, specific surface area, and metallic impurities were the largest contributors of the oxidative stress. And so what that means is that we still are in the very beginning, and we don't really know a lot about these materials. By the way, if I just go back to this one here, for example, you see silica and titanium on the list. Well, a lot of people are concerned about nanoparticles and so forth. Well, you know that the biggest consumer, the biggest industry that uses nanoparticles is the food industry. Silica particles are used as a food filler. Ice cream, orange juice, ketchup. Why do you think ketchup is so thick, for example? Titanium is used in milk to give it white color. So, and this has been going on for decades. Just we don't know about it. And unfortunately, that these don't have much activities. So, I'll stop here and continue with the panel.
Just a nice segue from food and to Dr. Knowles.
Well, good morning, ladies and gentlemen. It's still the morning. I'm just about warming up, and blood is circulating, slightly bigger than some of the nanoparticles I know we've been talking about. But thanks to the organizers, Sonia, for inviting me here. There's several people in the audience. We seem to follow each other around at various nanotech meetings around the world. So we're developing a nanotech club. Maybe we should formalize it. I want to make it very clear at the outset that I'm speaking on behalf of the CIAA. The second A is very important in this country. CIAA, not the Coca-Cola company. And this is I'll make a disclaimer now, which I make in all presentations, particularly in Europe, in that as far as we are aware, none of the food companies in Europe are using nanomaterials. Now, I'll talk just about the last comment. Engineered nanomaterials, including Coca-Cola. What was said about silicon dioxide and titanium dioxide, actually titanium dioxide is only allowed in food because it's white, and it's white because it's not nano. Silicon dioxide primarily is not nano either, because if it was, it would have to go through a separate evaluation program, which I'll show you in a minute, for all materials which are not conventional materials. But of course, at the tail end of the distribution curve, there'll be some, no doubt, some nanomaterials there, but the bulk is way above what we consider the 100 nanometers cutoff point. But anyway, just a comment I couldn't resist after the comments of the last speaker. The brief presentation I put together at the request of Sonia was really to deal with materials as we theoretically would see them going through the evolution from the laboratory to commerce, as I made the statement at the outset. This is theoretical because there aren't any, with the 2 exceptions in the packaging area in Europe, nanomaterials authorized for use in food in Europe, engineered nanomaterials. So I'm going to go through the potential applications, and I hope that slide will come out because my secretary told me when she was going through this, it doesn't look very clear, and we scanned it from a publication that I use frequently. So I apologize if it doesn't come out too well. They will look at the EU regulations very, very quickly on food and packaging, then some examples for additives, what we have to do in terms of approvals and packaging similarly. And then EFSA is, I'm sorry, we use acronyms a lot, the European Food Safety Authority. That is an institution in the EU which provides scientific advice on food to the Commission, which is the civil service of the EU, and a particular directorate, the Directorate General for Health and Consumer Protection, SANCO, which is the acronym for the French name for that. And then what we're doing in terms of communications with consumers and other stakeholders, which is extremely important. And last but not least, and Linda mentioned this in the list of her Institute's publications, the USEU regulatory convergence that we've been looking at for a while. So I don't know whether that's come through clearly enough, but you get the point that in agriculture there are applications, and these are some of the theoretical applications. As far as I'm aware, none of these are approved in Europe anyway for actual uses. The food processing, again, these are hypothetical uses. Of course, industry is looking at the potential applications in its research and development laboratories. All the big companies are looking at these. And remember that we don't manufacture nanomaterials. We buy them primarily from the chemical industry, unless we're producing nanomicelles or nanoemulsions in situ, so to speak. So we're looking at these. And of course, food has contained naturally occurring nanomicelles forever. And in the digestion process, you convert your macromolecules through a nano size before they become absorbed. So it's not a new particle size as far as food and the body is concerned, but we're talking now about what we call engineered nanomaterials to separate them from naturally occurring materials in Europe. And I want to separate the supplements industry also from the food manufacturing industries. That's not part of the food manufacturing, at least not in Europe. I know it comes under the FDA. It also comes under DG Sanco in Europe, but not the part that controls food manufacturers. But there have been applications commercialized and are on the market, I know, in this country, and have been through, some of them have been through FDA and got approvals. You can buy them off the internet in Europe. They're not actually legally regulated there. They're not approved, but they are available. Talking about general regulations on nanotechnology versus specific regulations, we, the food industry, and the Commission believe that the existing regulations in the European Union control the prior approvals which are required before materials can be put into commercial use. So we have the Novel Foods Regulation, which is still struggling with the definition. It had a draft definition. It was discussed some while back, and it's been referred back to two advisory committees for them to consider how to define novel foods. Sonia mentioned this in the opening speech. It's still a problem. We thought the definition was not too bad. It covered the size and the properties in one definition. Of course, you could shoot holes in it if you wanted to, but it was pretty general, and we thought, given the difficulties of coming to an agreement on a very specific definition, it was a good compromise, and it had a caveat that when there was an internationally agreed definition, that would be incorporated in the law. So we believe that all of these potential areas of applications of engineered nanomaterials cover the prior approval which is required in Europe. And there's one I've missed off here, and that is the General Food Law Regulation, which covers the marketing of all types of foods. And like all countries, General Food Law says all food placed on the market must be safe. I'm sorry, I apologize for my voice. This is something that some passenger on the flight over here a few days ago, I think, contributed to me. No doubt a nanoviral material that was transmitted in the air conditioning of the plane. And it should have had a title. I had this slide modified in Atlanta of food additive approval, but as you see, it's obviously about food additives. There's again a learning process, and we heard about this earlier today, of how to assess the risks from engineered nanomaterials. There is a large research program, which I'll mention briefly, in the EU on the safety of these materials from not only food applications, but from all potential applications where individual nanomaterials nanomaterials, nanoparticles may be ingested or inhaled, or obviously with cosmetics we put on the skin deliberately, and their absorption, metabolism, distribution, and excretion is being looked at in these programs. And there will be some years before we really are in a state to say, yes, we've got enough science to make the kinds of approvals that we need to make for some of the materials. A food additive has to go through, whatever the food additive is, through a formal approval process. In the European Union, there is no GRAS, which you have in the US, which is the generally recognized as safe system. In case you didn't know what that acronym GRAS is, GRAS, just one S in this case, which is used widely for self-evaluations by companies and then notification to the FDA, who looks at that. And we have to evaluate everything. So there'll be a comparison of the conventional material with the nanoscale material, and it's a case-by-case evaluation, and we will, in theory, submit all the data that the European Food Safety Authority has suggested in its very general guidance for nanomaterials, which again I'll mention in a short while. And then it'll be approved, or it won't be approved, and it'll be approved almost certainly with very specific specifications for that one size range of nanomaterials. And if you make the same material in different size ranges, smaller nano, then we'll have to go through another safety evaluation, which is very clear. Similarly for packaging, and we have a regulation you saw on active and intelligent packaging, and primarily it is to do with, again, it was mentioned, coating them with nano antibacterials or with sensors, again through an evaluation process. This is just a reference to the guidance for risks from nanomaterials from the European Safety Authority. This is just one small part. They're recommending, of course, that you have to also understand the chemistry, the surface chemistry of the material, interaction in the food and feed and the gut and in biological tissues, etc., and detection methods also should be supplied. Communication with stakeholders. This is just we had a meeting, as you can see, the 23rd of March, not too long ago, and I chair these every year. The Commission has similar ones called Safety for Success, to do with nanomaterials, where the same stakeholders are all invited. These are just some of the items we discussed in March with our different stakeholders, consumers, NGOs, anybody that has an interest are invited to these meetings. We had just over 100 people at this meeting, and you can see we try and introduce them to the developments which are still in some cases a very early research stage. Sometimes they've actually reached pilot scale and some limited applications. So we are talking to the public. We are trying to ensure that they understand what is happening. We don't want to have the same problems that we had in Europe with biotechnology, GMOs, where there was very little, if any, public dialogue. We've learned by our mistakes, and so far, I think everyone who goes to these meetings is very pleased that we are actually holding them. This is the report that Linda had as you can see she's the first author. I was one of the people who contributed to the report. This is it. If you're interested, I'm sure you all are, since many of you are lawyers, in the different EU, US regulatory approaches to nanomaterials, nanotechnologies, primarily food and cosmetics, by the way, here, not electronics. I think it's well worth buying. I couldn't, because I didn't have time to get permission to abstract pages from it. It's got copyright from Chatham House. I have the address for the specific project if you're interested, and I think it's very interesting reading for those of you who haven't already read it. So that is where somebody mentioned, yes, our colleague from the University of Geneva, global regulations. What really we're talking about here is having regulations, and I think Diane mentioned this, which are mutually acceptable to the various countries, are mutually recognized as being adequate protection for the population, for consumers, or whatever the
really appreciate being invited here today to talk to you about QD Vision and what we're doing with quantum dots, responsible development, and global governance. I think one of my roles here is being a sole case study of what nanotechnology products can do, and also what the companies doing that development can do on the front side. Referencing some of the things that Rick talked about earlier, referencing the promise of nanotechnology, it's important to keep that into the story and into the debate. So this isn't marketing, this is education, but it's marketing. What I want you guys to understand about QD Vision is that we're a green lighting solution provider. So we think we're positioned to deliver a game-changing opportunity in delivering low-energy lighting, the most power-efficient lighting that's on the market today. These are products that we're shipping. The technology comes out of MIT. Myself and a team of scientists spun it out back in 2004 and 2005. It's a venture capital-backed company. We're about 70, 75 people today. And from the very beginning, we've had a policy of responsible development. We've had numerous, and I'll tell you about some of them, EH&S collaborations with universities and government. And we've used that to show the strong environmental benefits that the technology can bring. There's three people in that picture, and you all recognize my co-founder, Vladimir Bulovich, in the middle. To the left is, from your point of view, is the president of MIT, Susan Hockfield, and the other guy is the president of the United States. He's holding his hand under the most energy-efficient light bulb in the world, and that's enabled by the quantum dot technology that QD Vision puts into there. We sell what we call an optic into Nexus Lighting, which is a US-based company, publicly traded, that puts these bulbs on the market. And you can go to nexus.com and buy them today. I encourage you to do so. So clearly the president has an interest in energy efficiency, and here's why. Just without getting into details of what lighting is all about, there's two things that consumers and buyers of lighting should care about, amongst others, but two of the most important are power efficiency and color quality. Incandescent is what we've all had around for a long time. Edison invented it, or you can argue that even, but QD Vision actually recently won an Edison Award just a couple of weeks ago for Best New Energy Product. But this is a great technology. It mimics the sun. It's a black body emitter. It has the small problem of most of the energy it emits being in the infrared, and so the efficiency in terms of light that humans perceive is very, very low. But the color quality is excellent. It does a great job of mimicking the sun, which is what we're all evolved to be under. Fluorescent and compact fluorescent, much more efficient. But if any of you have bought these, taken them home, I look at Jeff because the EPA has completely switched over to CFL, and it's pretty horrible. I mean, the light quality is bad. They take a while to warm up. They flicker. And so a lot of consumers are buying them and then unscrewing them, putting their incandescents back in. You're starting to see legislation forcing you to not use incandescent. And the bottom line is governments need to force you not to, right? Consumers like incandescent bulbs because of the color quality. The EU, you can't buy an incandescent bulb over 100 watts today, and that's going to flow down to lower wattage products. It's already on the books in the US and Australia, amongst others. And so LEDs are being hailed as the next generation lighting technology. It's even more efficient and gets more efficient every day, but the same color quality problem persists. So what people are doing is they're adding what's called a red phosphor material to improve the color quality. As a result, it loses about half of the efficiency. So you've got this great energy efficient product. In order to make it acceptable to consumers, you have the efficiency. And so instead of using red phosphors, which, by the way, utilize europium, which 99% of the europium supply in this world is dominated by China and Russia. So instead we use quantum dots, which is the luminescent material of the Western world. I coined that myself, if it wasn't obvious. So if you use quantum dots on top of a cool white LED, you can get the color quality almost as good as incandescent, essentially equivalent to incandescent, while maintaining color efficiency. So The Economist, just about 2 months ago now, did a great article and video piece. So I really encourage you guys to spend the 7 minutes. Go on theeconomist.com, look up quantum dots, and you'll see this 7-minute video. And it walks you through the history of light, but it walks you through what fruit looks like under incandescent bulbs versus LEDs, right? And so you thought apples were red, but they aren't anymore. And then you put the QD optic back on, and apples can be red again, and grapes can be red, and all sorts of, hopefully things that aren't red they shouldn't look red. But once again, you can render color appropriately that humans might want to live under it. So I'm going to skip technology, but this is classic nanotechnology. These are particles we synthesize from the bottom up, so the nano manufacturing principles are certainly applied here. These are very small, 2 to 12 nanometers. Most of them end up being about 5 or 6 nanometers in size. And the properties we're leveraging are because of the size. Okay, so no mincing words here. This is the reason these things glow and we can change the color and get the narrowband spectra and all the goodness is because of the nano. But the benefits are huge. So we talk a lot about climate change, and any sort of regulation of nanotech should be focused on protecting the environment, right? So what are the leading negative things in the environment? And we all talk about global warming and CO2 production and 22% of world electricity being spent on lighting. Right? If you had displays, which is QD Vision's next market, it's about 25%. So that's why you have governments forcing the conversion away from incandescence, but they're replacing it with technologies that rely on mercury, both in liquid and vapor form, and so there's all sorts of environmental implications of that weren't well understood when the conversion happened, and just poor color quality that humans don't like. So we think LED with quantum light optics can really eliminate that trade-off, or that decision point of, well, we can have good color that you actually care to be under, or you can have efficiency. Now you can have both. So this is what it looks like. We print quantum dot ink down on a diffusive color. It absorbs some of the high-energy blue light that the LED produces. It down converts it. This isn't rocket science. It's quantum mechanics, but it isn't rocket science. It's well known how to do this stuff now. And we just tailor the light. We engineer the light spectrum to mimic that of the sun. The result is 2700 Kelvin warm white light, 90 plus CRI, so that's color rendering index, how closely the light source renders light compared to the sun. So we're getting 90% or better, which is considered museum quality lighting. And we're doing it at 60 plus lumens per watt. So the next best product on the market at this color temperature and color rendering spec is 42 lumens per watt by Cree. So it's 50% better than the next best product on the market, thanks to nanotechnology. And there are real environmental net benefits of doing that, right? So it's not just the product gets to say it's higher lumens per watt. It reduces the cost of light to our customers. It reduces electricity consumption by 80% if you're replacing an incandescent or halogen bulb. You're reducing mercury in the product by about 25 milligrams because of the long lifetime of this bulb. It's actually equivalent to buying about 5 CFL. Of course, the energy consumption goes directly to CO2 emissions because, for the most part, electricity is produced by burning coal in this country and around the world. There's less manufacturing waste because it's one bulb for 15 years if you run it at 12 hours a day. And the largest benefit is you don't have to force consumers to buy this. Right? This is something that they'll want, and the degree of market uptake will determine how fast you can eliminate the CO2 production or mercury production or whatever you want to track because of lighting energy consumption. So QD Vision, since we founded the company, has really embraced this idea of responsible development or safe development, it was referred to as earlier. And this isn't something you do at the very end, right? This is something that is a part of all aspects of the product design, product life cycle. Worker safety. I'll talk about some of the studies we did with NIOSH, environmental safety, some of the fate and transport studies we've done. But the key aspect of this is it's got to start at the beginning. It can't be develop a product, put it on the market, and then put some lipstick on the pig. But I also want to state very clearly that there's health and safety considerations that you all are very concerned about, and it's limited by the lack of literature on these materials. It's not very well understood what exactly is going on in the body or in the water supply when you get these things in there. The quantity of material we need to do this is minuscule, and so we argue very strongly that the effects cannot be great as a result. But there's a gap here. There is a knowledge gap, and that's why I was down Tuesday at the National Academies of Science talking about EH&S research strategy needs in the U.S. So just some of the things that we've done here to give examples. I think Public debate is a big part of this whole topic, and public-private partnership is a big part of this project. And so here's some examples of how that can happen. Back in 2006, a lot of you, I'm sure, are aware, US NIOSH, Occupational Safety and Health, had a voluntary program, QD Vision. We were about 8 people at the time, but QD Vision participated in that study. A couple of Chuck's guys, Mark and Kevin, for those of you that know them, came into QD Vision for a couple of days. So again, at this point, they're 20% of the people on site, right? And used all the best known technology for looking for free nanoparticles in the air, nanoparticles on the surfaces, any trace of any migration of the material that could be accessed by our workers, and found none. We used that to establish best practices for R&D labs using quantum dots, and presented the results both domestically and internationally. Mike Ellenbecker, you heard about TURI, Toxic Use Reduction Institute, and so we've collaborated with Mike over the years to understand product safety and access some of the state-of-the-art nanoparticle detectors that he's developing. So, taking it straight out of the lab and putting it into an industrial environment and making sure we don't have particles. And really doing the unnatural things, taking a product that's meant to sit in your, oh man, I'm going to run out of time. Okay, thank you. Maybe the thing to really focus on for this group is our collaborations with EPA. So this material is, in our opinion, and in the EPA's opinion, regulated by TSCA. We did need TSCA approval in order to, actually I think I have a slide on regulatory. There you go. So, we did seek TSCA approval before it was honestly black and white whether or not a quantum dot should be considered a new material. You could argue it's a smaller version of an old material. But we did receive that approval. As part of that process, they recognized the material as pollution preventing after doing the analysis of all the things that I just mentioned to you. And we're continuing to work with those guys, and I guess I want to put you all in their shoes, right? So their job is to protect the public from this, but if they just regulate indiscriminately, if anyone in the world regulates indiscriminately, plays it safe, as it were, then it's very clear what happens. It just doesn't get produced in the U.S., right? And jobs is something that we all should care quite a bit about as well. And it's not that QD Vision will go out of business. It's just that we'll make it somewhere else. And that's a business decision that needs to be part of the discussion. And it's in our best interest to get these things right, to be able to make them here where we're all based, et cetera. And so that's why we engage in these discussions so clearly. But the sort of the next level down is, okay, so we can make quantum dots. So now our process changes by 5%. Right? We need to add a little bit more to get the efficiency higher. We're continually making improvements, of course. We're largely an R&D organization. So do I need to apply for approval again? Right? So if I do that every time I improve my process, then Jim Willis and Jim Allwood over at the EPA are going to hear from me every week. Right? And that will completely shut down the process. They simply don't have the resources to do that. So we needed to come up with ground rules for when a QD Vision quantum dot becomes a new QD Vision quantum dot. And again, we engaged in discussion. We led educational forums down there. We had several meetings. We helped them draft what is now a working draft of policy that we're living by. And it hasn't been made public, so we're the only ones living by it. But hopefully that will become actual quantum dot policy that will be part of TSCA over the years. So good regulation is better than no regulation. That you heard that from Rick as a government organization, but I think it's important for you to hear it from the business perspective as well. I'd much rather know what's required of me going forward than not know. Right? I have to fundraise every time we run out of money, which is scheduled to be every 18 months or so. And I have to convince them that there's not some new rule that's going to simply put me out of business or out of business in this country coming down the pike. So certainty is something that's been brought up and is absolutely part of the need here. I like to remind us all that the goal is keeping the public safe while providing that hospitable, predictable business environment. If you have one without the others, there's no success here. I've actually, the Friends of the Earth got mentioned earlier, and I've actually been on a panel in Paris at the OECD sitting next to someone from the Friends of the Earth. And he felt very strongly that they should use the precautionary principle and not allow my product to market, even though there were some benefits. I said, okay, so it'll just be LED, right? I described to him all the unknowns about LED. He said, okay, well, it can't be LED, CFL. I described to him all the problems with CFL. He said, okay, well, CFL's no good either. We'll just stick with incandescent. You know, all the CO2 that's produced, great. He actually said, well, then maybe we should consider turning off the lights, right? So, you know, there's extreme positions out there, and it's all of our jobs to sort through them, come up with the happy middle that allows us all to live and work and get the benefit of innovation while keeping the public safe and not taking undue risk. There is a role for that word undue. With that, I'll wrap it up. Thank you for allowing me the extra time.
Thank you. It's a pleasure to be here. I've been asked to give you an update of progress in understanding and preventing work-related disease and injury from nanomaterials. I'm with the National Institute for Occupational Safety and Health. We're part of the Centers for Disease Control, and we are charged with conducting research and developing guidance in relation to workplace hazards. The basis for concern about the health and safety effects of nanoparticles comes from three evidentiary streams. First of all, findings from air pollution epidemiology have over recent years showed that increasingly smaller particles appear to be responsible for the respiratory and cardiovascular effects that have been found. There hasn't been good measurement of the actual nano component within this smaller category, but there is strong suspicions that it contributes. Secondly, studies of incidental nanoparticles, particles that aren't intentionally produced, that come from various kinds of industrial combustion activities, such as welding or from emissions from diesel products, show a wide range of health effects, including pulmonary and eye irritation, various kinds of fevers, and lung cancer. And then initial animal inhalation studies of engineered, purposely made nanomaterials have shown findings in terms of pulmonary fibrosis, lung cancer, mesothelioma-like effects, and cardiovascular effects. And so this is what got the public health community to have a strong concern about the health potential of nanomaterials. One other area, too, was that there had been some research showing that various kinds of nanoparticles can translocate, move from the nose to the brain, from the skins to from the lungs to most organ systems, and to possibly penetrate the skin. This is a small body of information, but it also added to the concern about the potential health effects. When you talk about nanotechnology and you specifically want to focus on the indications for workers, it's really all about the particulate, nanoparticles. And there are a myriad of possible nanoparticles that will depend on combinations of a variety of physicochemical parameters, so size, shape, surface coating, surface charge, functional groups, and many others. And so it's very hard to have an intelligent discussion about nanomaterials without continually caveating what you're saying, providing caveats about which type of nanomaterials you're talking about and which type you're not. Because the toxicity potential of various nanoparticles can vary depending on the combination of physicochemical parameters. So to give you sort of a quick update of the progress in looking at occupational safety and health problems, I'm going to look at it from the four major components of the risk management continuum. So what have we learned about the hazard? What do we know about exposure? What do we know about risk? And what kind of risk management guidance has been developed? So first of all, for hazard, and that's essentially the toxicology of nanomaterials. This is an interesting study that shows that in the picture you can actually see nanoparticles in lung material. And so certain carbon nanotubes given to animals by inhalation, the way workers might experience them, have been shown to develop fairly rapid and persistent fibrosis in the lungs with relatively small doses. Certain nanoparticles, particularly single-walled carbon nanotubes and titanium dioxide, have been shown in animals to cause cardiovascular dysfunction. And certain multi-walled carbon nanotubes and titanium dioxide have been shown to have impacts in certain regions of the brain. This is what we're finding with inhalation studies. We're also finding, and this is quite disturbing, this is a picture of the pleura of the lung, and this is the pleural space outside the lung. You can see that we have a picture of a fiber that was inhaled that worked its way through the lung to the pleura and the pleural cavity. This is what asbestos does. And so that gives us concern that if a fiber with a certain long residence time in the body can penetrate through to the pleural space, that it could possibly have the same kinds of effects as asbestos. Clearly, though, there is other research that shows that you could possibly modify that fiber in some way, that it might not have those effects. And so we're not saying that there's a balance there, but we're saying that there are other factors that need to be assessed. Exposure. What do we know about exposure? You heard Diana Bowman say earlier that they didn't know in Australia the size of the workforce. We don't know the size of the workforce in the U.S. We don't know what kind of exposures are going on, for the most part. Until recently, you could count on one hand the number of scientific publications with real exposure data that were available. Now there's a slight bit more. NIOSH established a field team that went around to work with companies such as Seth just talked about with his company to try to learn a bit about what was going on in different kinds of workplaces. And when you talk about workplaces, and in this segment from lab to market, there are workers in all aspects of the life cycle. So the research scientists and the lab people are workers all the way to the people at the end of life. And so we've gone out to a lot of different places. You can see in this many laboratories, but some manufacturers. We've identified different kinds of carbon nanotubes. And generally what we found are what appears to be relatively low levels of exposure. But we don't know really what these levels of exposure mean because we don't know what the toxic potential is of these materials. And if they're more toxic, possibly a lower amount of exposure could still be significant. But these are generally low levels of exposure. We published these in recent literature. And then in terms of risk is when you have something that's hazardous and you have exposure and you're looking at the probability of a negative effect. And so we've been looking at risk of titanium dioxide. And again, this is risk for workers. This is not risk for population who might have titanium dioxide in their toothpaste. This is based on inhalation data with animals. We were one of the first agencies to differentiate between large-size titanium dioxide, here known as fine, and the nanoscale titanium dioxide, or ultrafine. And using animal data and projecting it to humans, we've made recommended exposure limits that are almost tenfold different in terms of the nano size to the versus the larger size. Similarly, looking at carbon nanotubes, specific types of carbon nanotubes used in the studies that we've conducted, right now there is no regulation for carbon nanotubes save in the workplace, save the regulation for graphite, which is clearly not adequate. And what we've found is that exposures that caused the damage in the animal studies that we conducted would occur in just 20 days exposure to the regulated allowed amount of exposure that could occur in the workplace using the graphite standard. So clearly the lesson here is that the occupational exposure limit for the large form of a material is probably not a good guide for the nano form. Nonetheless, in terms of regulation, the Occupational Safety and Health Act of 1970 is the predominant regulatory authority with regard to the health and safety of workers. And then lastly, in terms of risk management, the good news is we've had 100 years experience in controlling dust in the world, at least, where we've applied scientific methods. And clearly, we've had a lot of experience that we can borrow from the pharmaceutical industry, where they've had efforts in controlling biologically active dusts. And we believe that there is enough evidence to say that you can control in the workplace exposures to nanoparticles. It may cost a little more, but it certainly is doable. And certainly you can see some of the kinds of examples here. And this may account for why, when we examined various workplaces, we saw relatively low exposures. Now, clearly not all industrial processes that will use nanomaterials will be able to be done inside boxes, inside enclosures. And we're going to have to see, as these industries scale up and they make more industrial size kinds of operations, what kinds of controls will work. So it's not an issue of can we control, it's an issue of what is the efficiency of the control measures that we use. And with that, I think I'll stop there. Thank you.
No power and no point. Thank you. Is this loud? It's loud enough, yes. Well, I think I should begin with a sort of a true confession that my organization, the Center Group, back in 2002, I guess it was the very end of 2002, called for a moratorium against any further research, even in the labs, in nanotechnology. And certainly it called for the removal of products off the shelf that actually touched the skin or was in any way ingested by people or in the environment. And for making that call at the end of 2002, we had the, I think it was the Nano Business Alliance, accused us of being Maoists. Actually, the guy who accused us was didn't even know who Mao was, as it turned out. But and we became instantly rather unpopular. We'd also managed to organize our protest against nanotechnology in such a way that we produced a report at the beginning of 2003 called The Big Down, and that was picked up by the New York Times as the front page of their business section with about a half-page story about it, which then we were accused of deviously planning this, but it was entirely accidental. Prince Charles picked it up, and which is always a dubious thing as well. Support for Prince Charles is a bit risky. And Prince Charles picked it up and invited us to London, and we met with him and with the Royal Society. That led to pressures on Tony Blair to, remember him, he was the Prime Minister twice back, to actually call the Royal Society in to do its own investigation into nanotechnology. And then we followed that with a global contest for a nano safety symbol, which got a lot of international attention, and actually the winners were published in the front page of the Washington Post just the day of an opening White House meeting on nanotechnology. So by accident and good luck in some cases, I guess we managed to be fairly effective at getting the issue, at some levels at least, into the public consciousness and starting a kind of a public debate about nanotechnology even back then. I would still say that, by the way, the references to all of these things I've just mentioned you can find, and you can get the documentation on our website. It's free. The website is simply www.etcgroup, all one word, etcgroup.org. But the history is all there. We would still call for a moratorium on even lab research in nanotechnology and removal of products that get into the environment or affect the human body off the shelves. And I say that and go on to say that I'm an enthusiast about nanotechnology. I think there's a lot in nanotechnology that is exciting and important and can be very useful to humanity. And I want to see all of that go ahead. But so having made that contradiction, let me explain how we got to where we have our position and where I think things are changing in the future. And I'll try actually to simply make this the basis for trying to talk about where I think global regulation will be going in the next little while. And I'm a little bit optimistic about that, actually. We began to look at nanotechnologies as an organization back in 1999. We had our first international meeting about it in 2001 in Sweden with the Dag Hammarskjöld Foundation. We brought together scientists and policymakers from both sides of the Atlantic, from public and private sectors, to look at nanotechnology. Our entire focus in 2001 was on ownership and control of the technology. Who had the patents, who was investing in the research, where were they researching, what were the areas they were trying to develop, what would be the longer-term implications for issues like employment, issues like raw material supply, energy costs, and so on, for the world. In particular, because our focus has always been this, it was to look at the implications for developing countries, for Africa, Asia, and Latin America. We thought there'd be major commodity impacts, positive and negative, in developing countries, and they need to understand these issues from the beginning. It was only on the last day of what was a very amicable 4-day discussion that it occurred to us to ask the scientists in the room the question that, well, what about nanoparticles? Is there any concern about safety of nanoparticles? And I very clearly remember that last afternoon that there was sort of a silence from both sides of the Atlantic, and the response that we got back from everyone was, there's no problem. It's perfectly fine. Why would you be worried about that? And to be also honest, we completely believed them. We thought, okay, well, good, that's good. Our concern was, again, ownership and control issues. We weren't really thinking about health and environmental issues, about which I must guarantee you we have absolutely no expertise whatsoever in the organization, not then and not now. But within a few months, we were at a conference in South Africa, in Cape Town, looking at the implications of other technologies, in fact. And we met with a number of scientists from the National Nanotechnology Initiative in South Africa. And they told us that, in fact, they insisted that students working with gold nanoparticles wear spacesuits in the lab. And they routinely told them to watch out because this stuff should be seen as dangerous as Ebola. So be careful. Well, we were quite shocked by that. We'd just been told a few months before that there was absolutely no problem here, and suddenly the scientists working on gold nanoparticles were saying, we're not sure, we're kind of worried about it. About 2 months after that, I was in France at some meetings in France and met some scientists from the South, and now part of the Nanotechnology Center in Grenoble. And we're saying that, well, in France, their policy was to have everybody wear those subway-type masks that you sometimes put on, and which struck me as funny because, I mean, with nanoparticles, wearing one of those subway masks is a bit like having a basketball hoop around your head to keep the mosquitoes away. And yet, but they said that's what they did. And then I was in Houston a couple of months after that and ran into people in the private sector who said that they had a bare hands approach to nanotechnology and weren't at all concerned about that, and no one had any rules at all in the lab. That was also true of the university as well as private companies. Well, to us, that just didn't make sense. You can't have that extreme positions among the scientific community of some saying for the lab's got to wear a spacesuit and other ones saying don't have to wear anything at all. And as we talked to a few more scientists about it and felt, well, this is a bit crazy. What we've got to do is at least get it out there that this has to be a topic. It has to be discussed. So we called for a moratorium, including for the lab research. We suggested the moratorium would only have to last a few weeks. The scientists need to talk to each other on the telephone, have some conference calls, come up with some best practices, come up with a way of monitoring those practices so they could report into each other as they learn more about safety issues, and they go back into business again. When I look back on that from 2002 to today, I wish they'd followed our advice. It would have made sense. It was reasonable. I still think it's reasonable. We still don't have anything like the kinds of comments, as everyone has said today, you can't even figure out how to measure the stuff. How do you then determine anything else? We still haven't got there. It seemed to be only prudent to, in fact, take this very cautious approach. And if we were arguing that, well, but doing that, we would have stopped these wonderful new technologies from moving forward. Which ones are those, by the way? I'm glad for the lighting. That's good. And that wouldn't impact, except for in terms of the production of it, it would be, I assume that's a very safe product. But frankly, sunscreens, cosmetics, stainless clothing, why not take the time to do it right? Why not learn from the last century of botched mistakes and 30-year delays? It seems to be on average there's about a 30-year delay between when the first scientific reports come out saying, hey, there's a problem here, and someone actually acts on it. Recently we felt to say, well, let's start off from the beginning and get this right. We're not here jeopardizing humanity. We're not here taking at risk or stopping some major breakthroughs in pharmaceuticals or medical care which may or may not be the case down the road. Let's at least deal with it and get it right now. But of course, everyone's gone ahead with it anyway. And now we have thousands of products in the marketplace, and we're perhaps at that point where it's going to be almost politically impossible to really have good regulation at the global level because too much is invested. Since we made the call for a more cautionary approach to nanotechnology, the world has spent about $50 billion in research in nanotechnology. And at that point of investment, common sense goes out the window, commercial sense is all that counts. I remember in meetings with the Royal Society in the UK talking about nanotechnology even a few years ago, the mantra that everybody used was the same statement, which is that don't you realize that there are more scientists in Beijing working on nanotechnology than there are in all of Western Europe, at 1/20th the cost of a Western European scientist. In other words, health and environmental issues aren't really important, folks. What we've really got to do is address the question of the race of who's going to get there first. In that context, I feel deeply distrustful of the efforts that have gone forward so far to try to establish regulation. The good news, and we've been part of every discussion over the last several years, from ICON and Houston and CBAN's work and so on, there was a nanotechnology for the poor initiative the Rockefeller Foundation launched. We had discussions in India on water nanotechnology, and Brazil on raw materials and nanotechnology, in London about sort of wider sort of regulatory aspects of global regulation in nanotechnology. We've been in all those discussions, yet it hasn't really led to anything very useful in terms of real practice or real activity. We still are more or less where we were back in 2002. The change that I'm a bit optimistic about is that a couple of years ago, almost 2 years ago now, SciChem, and now I think it's converted itself into the ICCM at the intergovernmental level in the United Nations, began to have a discussion about nanotechnology. I was able to attend the first meeting in Dakar, Senegal, almost 2 years ago. To my amazement, the regulators there from Africa and Asia and Latin America in particular did catch on to the fact that this was not only a potentially important and useful technology, but it had to be introduced correctly, and they had to be careful about how it was introduced. So in fact, SciChem, now ICCM, had launched a series of discussions around the world about nanotechnology. OECD has got involved in the act as well. And I was also at that meeting in Paris last summer. But I was in the agricultural discussion. Friends of the Earth was in the other one, I guess, on the LEDs. Okay, thank you. Anyway, I think what's been impressive from that process is that over the last few months, we've seen 53 governments in Africa say they want to have labeling of nanotechnology products and processes. 53 governments in Africa saying that they want to monitor the technology closely, they want to understand it better, and they don't want to be simply taken advantage of in the process. And the same thing has happened in Latin America. At a meeting a few weeks after that, Latin American countries said exactly that they want to have labeling for the technology, they want to have it tracked and dealt with globally. Okay, I'll end with one thing. I would not propose there be special regulations or special covenants or codes of conduct related to nanotechnology. Frankly, I think we're way past that. We need to have at this stage is an international convention for the evaluation of new technologies. Not just nanotechnology, but synthetic biology, geoengineering, all of the new things that are robotics and so on, they're all coming down the track. Industry and government and civil society need to work together to establish a broad, open way that we can evaluate new technologies, see them as they come, put on the red lights, green lights, and yellow lights as we need to, as they move from the lab down the path, so we make sure the best stuff moves forward as rapidly as possible, and we're careful about the rest of it. And do it the best way we possibly can, as carefully as we can. Frankly, just dealing with nanotechnology at this stage just doesn't make sense to me. Thanks very much.
Hi, Mark Banish, VP for Quality and Regulatory Affairs at NanoComp up in Concord. First, I want to thank Seth for what I think was an excellent and very comprehensive and considered approach to EHS issues. I like to think that my company, which makes carbon nanotubes, in my own person, has the same approach. One thing I would like to put forth here is that companies in the nanomaterials space are often startups and are often started by professors who have a certain mindset or perhaps a lack of experience. And many of these startups do not have the breadth of experience or the insight to consider EHS as part of its development. And I'll use Seth as a good example of a possible exception. But I'd like to know what people think about that, about dealing with EHS issues in these types of environments where you may not have project management plans and the type of basic rote prescribed development where these types of issues would emerge.
Well, I was just going to actually follow up on what Seth said. Our center provides services, and actually Mike Ellenbeck is part of our center, and he also worked with NanoComp to help them. He took his particle counter that looks at exposure down to 5 nanometers, and he went and we tried to help startups and small companies to meet not only to make the work environment safe for their workers, but also to help them meet some of the EPA, for example, requirements that make sure that there's no exposure, at least that we can measure in the work environment. So I think there's a need for something like this for a lot of the small companies that are startups because they don't have the equipment, they don't have, in many cases, they don't have the expertise, and so we try to serve that function at least to support some of the companies, at least the local companies here in the Boston area and in the state.
And just to follow on from that, we're quite concerned about lab workers and workers in startup companies just for the reasons that have been mentioned. They're not having the experience as well as not having the consciousness about occupational safety and health. And so indeed, that is an area that needs input. That being said, I think there is great evidence among the various companies that we've looked at and are aware of and seen around the world that there is an embracing of the precautionary principle as far as dealing with the health of workers by many employers who are venturing into nanotechnology. They realize that you can hurt the whole development of the technology if you're not protecting the workforce. And so I think there is a broad adoption of a lot of precautionary principles. Clearly more could be done and some areas need to be codified, but many investors and employers say they would rather have a fair regulatory framework to work in than not have one. And to that end, they've been starting with adopting a precautionary approach, and we certainly salute that.
Can I just add, from a European perspective, the European Union Commission produced a code of practice or guidance, whatever you want to call it, for research workers quite a few years ago. And then it's built on this by working with the member states, many of which, particularly Germany, which has the large chemical industry, for, again, good codes of practice for manufacture of these materials. So I think right from the outset, certainly because of the dialogues we've been having, as I said, over many years with many stakeholders, the understanding that that's, and I hate to use the word precautionary principle, the term precautionary principle, because it's such an abused concept, but that has been the underlying way I think we've all been moving forward. And there have been many discussions between the US and the EU on how to move forward together, not only in terms of consumer and worker protection, but also in terms of making sure that we don't inhibit trade. Because you said you can manufacture somewhere else. We say the same thing. You know, if we get blocked in Europe with restrictive regulations which are not science-based, you know, the mantra is we'll manufacture somewhere else. I'm not sure where we're all going to manufacture at the end of the day, but seriously, I think that we have tried with Nanotechnologies to take a global approach wherever that's practical to ensure that there is an understanding across the world on risks and opportunities.
If I could just follow on just briefly. That being said, that there is a move toward taking a precautionary approach, I think since we're at the front end of a new technology, society has to invest more in assurance that these approaches are working. And so we need to consider such things as the development of surveillance programs and exposure registries for the workforces that are involved. And we haven't seen that quite yet, though this summer in Keystone we're having a conference to address that issue. But it's clearly one that needs to be considered. We have to go the extra mile with a new technology. And I think there's a lot of agreement in that, and we need to pursue that.
It's sad, though, that as we started out with nanotechnology in the 90s, at least, the world gave itself a kind of frontal lobotomy in terms of the capacity to actually regulate new technologies. We had, through the United Nations Center for Science and Technology for Development in New York, which was there to give advice to developing countries, to track new technologies. It was cut and killed in the mid-90s. We also had the UN Center for Transnational Corporations, also in New York, that was there to track the companies that were producing the technologies as well, to give advice. That was also cut and killed in the 1990s. So that there's no global ability among the nations of the world to actually monitor technology at all.
My name is Robert Lindefeld of Nantero. I wanted to make a quick comment on Dr. Toomey's statement about the technologies that may not warrant a lot of respect from the consumers. The part of the problem is right now, the number of companies, including Nantero, is working on nanotechnologies. That's all we do is carbon nanotubes. The technologies that are coming out are going to be tremendous for humanity. We can make sensors that can line subways to sense the instant that somebody walks into a subway with cyanide. You can sense that. International space travel will not be possible without carbon nanotubes. We put our carbon nanotubes out in outer space on the space shuttle Atlantis last May. Came back down 100% yield. If you want to use traditional CMOS technology, you're not going to do it unless you employ new technologies. So carbon nanotubes and nanotechnologies are going to save a tremendous number of lives, are going to permit our humanity to evolve beyond a point where we are now. So it's not just about making shampoo better.
We had a meeting of governments and science and industry in Madras. Now it's no longer Madras, Chennai, in India. A couple of years ago, we looked at, again, how could nanotechnology benefit the poor. And it was an interesting discussion because we focused on water, exactly, and there's been a lot of work in nanotechnology and water purification systems. We looked at models from South Africa, Namibia, to Brazil, and Guatemala, and India itself, and so on. Conclusion from the scientists that were there at the end of the day was it was actually more efficient and effective to fold a sari over 3 times and pour the water through that than it was to use anything else.
Let me just say one more thing to comment on this, and actually the filtration is sort of a low level, and also the electronics doesn't touch a lot of people's lives, so a lot of people don't feel it, even though it has a very valuable impact on the technology in general. But I think one of the things that are going on in Europe, for example, is cancer therapy using nanoparticles. And this is done using magnetic nanoparticles as well as gold particles. And there's human trials that have been going on in Germany right now. And the initial results look very, very promising. The survival rate has been increased, for example. And the nice thing about it is that it's not expensive, because all they have is just inject the particles. They apply magnetic field, for example, for that case, or apply infrared light for the other case. And it becomes a very effective cancer treatment that only kills the cancer cells, and it has no side effect that we know of, because they're following the patients in the human trials that are going on in Germany. And it takes 1 hour, and the person goes home, and then the particles have been seen going through the kidney and flushed through the system. So that's one technology that touches all people's lives, and anyone who has sort of chronic disease or cancer and so forth. So it certainly has a lot of promise, and we haven't. But I think at the same time, we have to be careful. We have to be cautious, and we have to make sure that we know whether these materials are toxic or not before we use them in shampoo or in food or in treatment, or in products where they would come out of the products. For example, the examples at Nantero, actually these things are in chips. They're packaged. They will never come out. They will never harm anyone. So they're basically fine. They will only have an effect maybe if they're dumped and go in the environment. And then we also have to look at that, for example. So all these issues are very, very important. Just one comment about Mr. Knowles about the silicon dioxide particles. Actually, if I used to make silicon dioxide particles 25 years ago, before there was internet, before there was web, before there was anything. And the fumed silica you buy that goes into the foods is actually diameter size between 5 and 15 nanometers. And he may have been talking about the aggregate size, where they agglomerate, and they could be micron or a few microns. So actually the food that you see, I don't know about Europe, but in the US certainly does have these nanoparticles. Fortunately, the test that we have done, the test other people have done, that these silica particles are not harmful. They don't kill the cells, at least. That's a...
I'd actually like to hear Mike to say something about what seems to me a contradiction between the movements being taking place in Brussels in the European Parliament and the movements being taking place in the Commission. Earlier this week, we had the committee, the Environmental Committee of the Parliament, almost overwhelmingly expressed sort of concern about nanotechnology and demanding more regulatory initiatives quickly. Last year, we had the European Parliament almost unanimously vote for regulations within 2 years on food and nanotechnology. It doesn't seem to be the same message that you're reporting from the Commission itself.
Well, the vote this week was on the novel foods. It was on specific aspects. It's the second reading of the novel foods regulation. Now, the novel foods regulation has a specific clause in it about nanotechnology already. So they're already voting for what they've already voted on before, and it's already in there. What they were discussing was also cloning, which was really what the major emotion was about. Nobody wants cloning in Europe, at least in the Parliament. So the Parliament, of course, it gets very concerned about these issues, and when it gets into the member states, the Commission, then the Parliament's view is discussed, and as always with the European Union, a compromise emerges at the end of the day. But the regulations I listed all catch nanotechnology. They catch any new technology, particularly novel foods, that changes the current specifications of the material that's regulated. Even if it's produced by conventional methodology in a different way and changes the specification, then it has to go through another safety evaluation. It may only be a paper exercise, it depends what the changes are. But for nanotechnology, it's already foods regulation, because of the Parliament, also has a comment about including nanotechnology as a process that needs to be regulated. So, and the other overwhelming was not a regulation, it was just a report someone produced. And of course, yes, they said we need regulations on nanotechnology. Then it was pointed out to them, we already have them. The regulations are already there that control nanotechnology through all of the food side. I can't speak for the rest of the industry, which is why nanotechnology, and the fumed silica, by the way, was actually a presentation from the major manufacturers in Europe who were talking about the distribution. You're talking about the bottom end. The top end is above the 100 nanometers. And fumed silica has limited applications in certain parts of the food industry. Titanium dioxide is often quoted, but you can't use nanoparticulate nanotechnology, titanium dioxide in food because it's not white. And titanium dioxide is only approved as a white color. Cosmetics are a different story altogether for the sunscreens. So, I mean, all of these have been debated in the Parliament. And of course, we have to take account of the parliamentary discussions in the Council and the CIAA and all the other trade associations relevant to the industries input into those debates as well. So we do have a and of course, BEOC, which is the European Consumers Association, all input into the debates. So the Parliament is not alone; it's just one of the debating chambers that we work with in Europe. And I think we'll all benefit at the end of the day from having this public-private, if you want to call it that, partnership in debating these issues within and without the Parliament. We have the MEPs coming to our discussions. We invite them if they want to come and take part too. So I think with nanotechnologies in Europe, we are trying to ensure that we have not just one debate as the Parliament has, but we, with the Commission, on our sixth debate now on this subject, and that we continue to have them at least twice a year.
My name is Brooke Baker. I'm a professor here at Northeastern. I wanted to raise a question. It might come up in the intellectual property discussion, but it didn't seem like it, which is in response to something that Seth said about protecting confidential information and the contradiction of that commercial interest in this particular context of dealing with precautionary and safety concerns in a new technology. It seems to me that following the traditional model of protecting as a trade secret the information that a proprietary company develops in developing a particular product is hugely problematic in a new technology area, where you need is open source collaboration about dry holes, safety problems, good processes, etc. And then also, even in a regulatory sense, the issues of whether you can reference or rely on that data for subsequent approvals. And it seems to me that there should be a discussion, not just with respect to nanotechnology, but with the new technologies more broadly, but nano in particular, that the corporate or commercial interest in protecting the proprietary information from use by or regulatory reliance by another commercial entity greatly undermines the risk of openness and shared knowledge for the development of a new technology and for safety in general.
Yeah, I'll try to respond to that first, to the extent I understand all of the question. This gets raised all the time. It's an important issue, and I think it's a very resolvable issue. In working with NIOS, for example, I mean, it was very important to us. We would not invite them in if they were going to publicize everything they saw. Right? There needed to be some level of protection of our confidential business information. We are developing it, and continuously. It's not done, and we've patented it, and therefore it's no longer a concern, or it's not something trade secret that completely conflicts with disclosing our confidential business information. It's continually evolving, so we needed some measure of protection there. But in terms of, say, and we had that, and we were able to release, publicize, present. It actually was great because you saw reference to quantum dots and 2 to 8 nanometers and no detection as part of the charts that were shown. So you see that information is broadly, publicly disseminated. The useful parts of it that could be cross-pollinated to other people working in it, right? The generalizations that can be made. And so our need for CBI was not contradictory to NIOSH's need to establish best practices and broadly use them and apply them. In the case of EPA TSCA approval, right, we can submit the very lengthy form. We can mark certain sections of that confidential, and that's necessary for us. If getting approval to make our substance means we have to teach all of our competitors to make our substance, then going back to we're arm in arm on this. We'll just make it somewhere else. That losing your competitive advantage in a business, and we are in business. Losing your competitive advantage in a business to manufacture it in the U.S. is not a fair trade. There are other solutions. So we can mark it confidential. They get all the information they need to make a safety assessment, and we get the approval we need to go forward. Can someone else rely on that approval and not knowing the information, and there might be subtle differences in the way we make it versus one of our competitors make it? The answer is no. This is not a full PMN. This is a low-REX exemption or an LVE exemption, and these can't be relied on. Every company that wants to go and make quantum dots and rely on a low-REX needs to separately apply, and EPA has a chance to separately look at their particular process. It might be identical to ours, might be different than ours. They can't rely on my approval to approve their process because it isn't public. So, it's an important issue, but I honestly think it's very well addressed, at least in my interactions with the U.S. government.
I think Seth was speaking on both sides of that issue because I think his company is exemplary in being pioneers in this area. But I really think your point is well taken, that indeed intellectual property has been a barrier for us to get widespread penetration of the various employer associations and companies in various sectors. And indeed, until that is somehow addressed, I think it's going to be difficult to get the kinds of data that we need to really substantiate what's going on and anticipate where the problem areas are.
If I can just add that this is also under active discussion in Europe too. I appeared before a UK government committee last year, and this was one of the very difficult questions to address. We haven't found a solution yet on how we will address it, except to say that the work on safety assessment, the nanotoxicology, for want of a better phrase, is open. And of course, that is being funded largely anyway by a group of companies and more so by the European Commission, which is putting in several hundred million euros into toxicology research, and we all participate in that. And we believe that has to obviously to be open and transparent like any other basic science. But when that is being used by a company to evaluate a product and its manufacturing, then that's where it gets problematic. And of course, when in the food area that product has met all the commercial goals of the company and is submitted for approval, as Seth was saying, the same thing would happen. There'd be sections of the manufacturing process which would be marked confidential, but the whole safety evaluation aspects would be public. That is what we're saying. I mean, since nothing has been submitted to date, we don't know just how that's going to pan out, except for titanium nitride for use in PET, which provided the full safety data in a very, very transparent way. A U.S. company, by the way.
Hi, I'm Marvin Lewitton. I'm an industrial hygienist with the Massachusetts Division of Occupational Safety. As an occupational health and safety practitioner, I can quite confidently state that for every company like Seth's and Mark's that in effect is self-regulating, there are well over 100 companies that are, to say unconcerned might be a little strong, but certainly don't have the same level of concern with protecting, either their workers or the environment. And I think the challenge is to come up with some level of regulation that allows for the development of this technology while keeping it safe. And obviously that level would be quite different for, say, QD Vision versus some of the other companies that I go into. And I don't know how one gets to the point of figuring out kind of where that level is. But I think that that's critical. I mean, for every company that calls the NIOSH field team, and, these are obviously companies that are concerned and are attentive to the potential hazard. I go into any number of companies that are either clueless or really just thinking bottom line in a very short-term way of thinking. And I think there clearly has to be a level of regulation and one that's consistent, just that allows for planning on how you're going to go forward. But by the same token, I think that there are people who are relative, or a little bit dismissive of regulation and look at that as being, anti-development. And I think that would also be a significant mistake.
Yeah, and Marvin and I know each other well, but hopefully no one here took that. I mean, I said it in plain words. Good regulation is better than no regulation, right? And so I like the word you chose, that we're self-regulated today, and because there is very little nano-specific regulation, I would take a strong position that lots of the existing regulation, I gave you the example of TSCA, absolutely applies to nanotechnology and is being applied. Looking at what additional good regulation is required is a good pursuit. I think doing that without the scientific basis behind it is anti-development. Right? Doing it because people are afraid of the word nano, because Michael Crichton wrote a book, is not a good justification. Or doing it because sunscreen is the only product that you can